Okay, am I audible? Good afternoon to all. Am I audible? Can anyone inform? Am I audible? Is my voice clearer to you? Are you able to hear me? Can anyone inform? Okay, so I didn't receive any responses. Okay, you are able to hear me? Okay, then let us start. So today I will discuss Millman's theorem and Tellegen's theorem. So let us see what is meant by Millman's theorem. What is the statement for this Millman's theorem? So this Millman's theorem states that so when a number of voltage sources, okay, when n number of voltage sources are there, means more than one voltage source. So here you can see I have written some E1, E2, E3, up to En I have written some n number of voltage sources, okay, more than one voltage source, okay. So if there are more than one voltage source in the given circuit, okay, are connected in parallel with their internal resistances. So each voltage source has its own internal resistance. So internal resistance of voltage source E1 is R1, internal resistance of voltage source E2 is R2, internal resistance of E3 is R3, and internal resistance of E4 is R4, and so on up to the last voltage source, whatever you have, maybe the nth voltage source. There may be 2, 3, 4, or maybe n number of voltage sources, okay, in the given circuit. So with their internal resistances, if they are connected in parallel, then this arrangement can be replaced by a single equivalent voltage source. Okay, so here I can write E, I have written E, or you can write EQ, your wish. Okay, with a series equivalent resistance Req. Okay, so for that, to make it more clearer to you, so just see this circuit. So here in this circuit, what you can see, there is a voltage source E1. There is a voltage source E1 whose internal resistance is R1. Okay, another voltage source is there, E2, whose internal resistance is R2. Another voltage source is there, E3, whose internal resistance is R3. Okay, up to and up to En. Okay, some n voltage sources are there. So all these voltage sources, if you carefully observe, they are connected in parallel. E1 is parallel to E2, E2 is parallel to E3, and so on up to En. All these voltage sources are connected in parallel. They are represented along with their internal resistance. Means their internal resistance is also shown here. Okay, so usually instead of drawing a resistor here, we can write internal resistance value nearby to the voltage source instead of drawing resistors. So usually internal resistance are represented at the voltage source itself, okay, instead of drawing separate resistor. But here separate resistors are shown here to make it more clearer. But when you look at this diagram, it seems as if these are not the internal resistances. These resistors R1, R2, R3 up to R, and they look as if they are connected in series to the source. Always remember, internal resistances can be represented in series to the sources. And sometimes in the question itself, they won't mention the, they won't draw any resistor in series to the source. If there is internal resistance to a particular source, they will simply mention some 20 volts comma 2 ohms. Okay, if it is mentioned like that, while simplifying the circuit, you can draw a resistor in series to that voltage source of 2 ohms. Okay, so that you can do that. So but here in the statement itself, they have mentioned that if n number of voltage sources are there, if they are connected in parallel along with the internal resistances, all these voltage sources E1, E2, E3 up to En, they can be replaced by an equivalent voltage source, E equivalent. Okay, and if n number of resistors, which are the internal resistances of these voltage sources are there, they can be represented by an equivalent resistance. Okay, so all the voltage sources are replaced by equivalent voltage source, that is E equivalent. All the resistors, internal resistances, okay, not resistors, separate resistor. These are not the circuit resistances, they are the internal resistance of these particular sources, respective sources. Okay, so these resistors can be replaced by an equivalent resistance. Okay, and after replacing all these voltage sources with an equivalent voltage and resistances with their equivalent resistance, you can connect that equivalent resistance and equivalent voltage across the load. So you see across AB terminals RL load is connected. Okay, so see in the this is our equivalent circuit. This circuit, what you can see on the right side, this is our equivalent circuit. So my cursor won't listen to me. Okay, again it has happened. Okay, whatever. So across AB terminals, A and B terminals, load is remained, it has been remained as it is. Okay, so load, we didn't make any modifications in the load. Okay, whatever load was there, you must connect as it is. Only the thing that you have to do is here you have to replace all the voltage sources with their equivalent voltage. Okay, you have to determine the equivalent voltage, and the equivalent and the internal resistances of these particular voltage sources must be replaced by their equivalent resistance. Okay, now let us go back to our statement. So what is our statement? When number of voltage sources, okay, are parallel, means they are connected in parallel having internal resistances, then they can be replaced by a single equivalent voltage source in series with equivalent internal resistance. Okay, and a load must be reconnected to this equivalent resistance and the voltage source across it. Load must be connected across this series connected equivalent EEQ, and that is equivalent voltage and equivalent resistance. I hope you have understood. I don't know. So I hope you have understood. Just write down this statement. You take a minute, write it down in your notes. So Milliman's theorem is applicable when multiple sources are there connected in parallel. Voltage sources are there which are connected in parallel. Okay. So this Milliman theorem, you know, it is applicable for simplifying the complex electrical circuits, and it is the combination of both Thevenin's theorem and Norton's theorem. And you can easily find out the voltage across the load and current flowing through the load using this theorem. You can even call this Milliman's theorem as parallel generator theorem. So I have shown you only the voltage sources connected in parallel. So this means this theorem is also applicable for the circuit which has the combination of both voltage sources and current sources. So if you people have completed writing this statement, just mention in the chat box so that I will proceed further. So I have one circuit here. So I have a circuit. This is it. You can see here in this circuit there are current sources, isn't it? Current sources are there. These are the current sources as well as voltage sources are also there. See. So this Milliman's theorem is not only applicable to the circuit in which voltage sources are connected in parallel, even the circuit can have both combination of both the parallel connected voltage sources and current sources. Okay, let us solve some numerical problems to learn this. Okay, before that, before solving the numerical problem summa, let us determine this equivalent voltage and equivalent resistance. How to determine this equivalent voltage and equivalent resistance? Let us see. Before that, you people, if you have written this statement, just draw this circuit in your notes. If you have completed, please inform. Draw with free hand. Don't use scale and all. Just draw with free hand. You will be able to complete as quickly as possible if you are drawing with your free hand. I'm hoping that you have completed. Okay, let us see. Now, the same circuit, I have kept it at the corner of this page so that you can compare and you can write the equivalent voltage equation. So, E equivalent is equal to, formula is, see in the first branch, this is our first branch. In the first branch, what is there? There is a voltage source whose value is E1 and resistance whose internal resistance is R1. So what is E by R? E by R is what? E by R is nothing but current, isn't it? So write E1 by R1. Okay, E1 by R1. Okay, E1 by R1. Okay, so that is current I value plus, okay, E1 by R1. Just write E1 by R1 plus next. Another, go to the next branch. Go to the next branch. What is there? E2 voltage source and R2 resistance. So what is, write down plus E2 by R2. That is another current. I2 current we can say. I2 current in branch 2. Similarly, go to the next branch. What is the voltage source? E3. And what is resistance? R3. Okay. So what is it? E3 by R3 is the current in this branch. So E1 by R1 plus E2 by R2 plus E3 by R3 up to En by Rn. Okay. Total how many, whatever voltage sources are there. Voltage sources are from E1 to En. E1 to En. Okay. So E1 to En voltage sources are there. So I am just writing the current equations here. Okay. So current in each branch. E1 by R1 is current in branch 1. E2 by R2 is current in branch 2. E3 by R3 is current in branch 3. Up to last branch. Current in last branch. Whole divided by, okay, whole divided by 1 by R. 1 by R means what? 1 by R means conductance, isn't it? 1 by R means conductance. So 1 divided by R. Okay. So here, first of all, write the conductance of first branch. Okay, what is the resistance in branch? Internal resistance of branch 1, R1. So 1 by R1. That is our conductance. Plus conductance of branch 2. That is 1 by R2. Next, conductance of branch 3. 1 by R3. At last, I go up to the last branch, that is conductance of branch N, that is 1 by Rn. So this is the formula that has been given by, means whoever has framed this theorem, he has given this equation to determine the E equivalent. Okay. So you can easily determine the E equivalent if you are using this formula. Similarly, you have to determine the R equivalent. Okay. So R equivalent is equal to 1 divided by G1 plus G2 plus G3 plus Gn. So there is no G. I didn't write any G here. G means conductance. I didn't write G here, but I am using the term G here. So you know reciprocal of resistance is conductance. So 1 by R is nothing but G. So instead of 1 by R1, what I can write is, I can write G1, G2, G3. I can do that. Okay. So I will just copy and I will write one more equation here. See, I have just modified the equation and I rewrote the equation here. So it might have been better if I am able to move this back. Okay, it's okay. It's okay. So you can even write R equivalent is equal to, instead of writing, I will just copy this R equivalent in the bottom. So this is it. You can see what I have simply modified this equation, isn't it? Above equation, R equivalent equation. So similarly, instead of writing 1 by R1, you can write G1 in the even voltage equivalent equation also. So see, R equivalent is equal to what? 1 by G1 plus G2 plus G3 up to Gn. G represents conductance. G means what? 1 by R. So R equivalent is equal to what? 1 divided by 1 by R1 plus 1 by R2 plus 1 by R3 up to 1 by Rn. So these are the formulae that you have to use to if your circuit resembles the Milliman circuit. Milliman circuits means if you have all parallel connected voltages along with the internal resistances, or the combination of voltage sources along with the current sources, then you can apply Milliman's theorem if it is not specifically mentioned in your question. If they have specifically mentioned, then you have to go for Milliman's theorem. Okay, so to simplify a circuit, you can use any theorem. You just observe how the elements have been connected. So depending on the connection of the elements in the given circuit, whatever theorems that you have learned till now, you can follow any of them. If in the question itself they specifically ask to simplify the circuit using so and so theorem, then you can't go for any other theorem. You have to solve the circuit using the theorem which has been mentioned in the question itself. Okay, so I hope it's these equations are very simple. Okay, so these equations are very simple. So E equivalent is equal to what? E1 by R1 plus E2 by R2 plus E3 by R3 up to En by Rn, whole divided by 1 by R1 plus 1 by R2 plus 1 by R3 up to 1 by Rn. Next, equivalent resistance R equivalent is equal to 1 divided by 1 by R1 plus 1 by R2 plus 1 by R3 up to 1 by Rn. Similarly, instead of R1, R2 up to Rn, you can write G1 1 divided by G1, G2, G3, Gn. So I hope you might have written it, and meanwhile, I took enough time to write down these equations. So I hope you people might have written already. So let us solve some numerical problems to understand better this theorem. Okay. So this is a numerical problem. In the question itself, they have clearly mentioned using Milliman's theorem. So you don't have any other option. You have to use the Milliman's theorem. Using Milliman's theorem, find the current flowing through each resistor for the network shown in the figure. So you have to determine the current flowing through each resistor for the network shown. This is our network. If you observe here in this network, in this branch there is a voltage source. In this branch there is a voltage source. What about this branch? There is no voltage source at all, isn't it? Only two voltage sources are there, but I can see three branches. Okay, I can see three branches here. Only two sources are there. So let us see what we can do. Just copy down this, just note down this circuit and write down the question in your notes. Just take a minute, complete it in your notes. So you just observe in this while you might be drawing it in your notes. You just observe here. They usually in the question itself, if it is a DC source, they must mention the polarities. Even if they didn't, they won't mention. You can mention them by looking at the positive terminal, negative terminal. You know the difference between how by physical difference between the positive and negative terminal. Okay, you can assign the polarities for these sources. Okay, I hope you have completed writing. Um, okay, so I hope you people have completed this slide, and you might have written it in your notes. You might have drawn this circuit and you might have written this question in your notes. So let us proceed. So what I have done here is, okay, so what I have done here is simply I have redrawn the given circuit. Okay, I have redrawn the given circuit. So see here, there is this resistor was earlier here, isn't it? Okay, so I have drawn it in just besides to this source, and I have given some notation to this source. EB1 is my notation, and this R2 I didn't make any change. Similarly, the resistor, this resistor R3, which was here, so I have changed its position. I have drawn it besides to this source, and I have given some notation to it, that is EB3. Okay, so now I have EB1 one source, EB3 one source. I don't have EB2. I don't have EB2. There might have been EB2. There is no EB2. They didn't give us. So always remember, if any resistor is in series to the source, it is just assumed that it is the internal resistance of that source. Okay. If a resistor is in series to the source, it is just assumed that it is the internal resistance of the source. Okay, so just redraw the circuit. So after redrawing the circuit, you just calculate the equivalent voltage. Okay, I'll just end and I will write here equivalent voltage. So what is our equivalent voltage formula? Here only 3 branches are there. So EB1 by R1 plus EB2 by R2 plus EB3 by R3. Of course, EB2 is not there in the given circuit, but we are writing because we have to satisfy the formula which has been given by Milliman's theorem. So according to that formula, we have to simplify. We don't have any other option. So that's why even though EB2 is not there, you just write it down. Later on, we can substitute 0 there. Okay, so EB1 by R1 plus EB2 by R2 plus EB3 by R3 whole divided by 1 by R1 plus 1 by R2 plus 1 by R3. Isn't it? Just now we have seen this formula. So only 3 branches are there. Okay, so only 3 terms will be there in the numerator as well as in the denominator. So just note it down. So what is EB1 value? What is EB1 value? EB1 is how much? 28. What is R1? R1 is 4 ohms. What is EB2? We don't have EB2. So what is EB2 value? It is 0. Okay, EB2 is how much? It is not there. So what is R2? R2 is 2 ohms. And similarly EB3 is 7 volts. And what is R3? R3 is 1 ohm. Okay, R3 is 1 ohm. So see, even if notations are not given, whenever you are simplifying the circuit using Milliman's theorem, you write your own notations and try to solve the numerical problem. So this is it. Now I hope you might have written. I'm going to the next slide. So what is it? E equivalent is equal to 28 by 4 plus 0 by 2. Okay, what is 0? EB2. EB2 is not given. We wrote on our own. Okay, we wrote some notation for that second in the second branch voltage source was not there. So even though we wrote on our own some notation, we gave some notation to the second branch assuming that there is some 0 voltage source. Okay, there is a voltage source whose value is 0. That's it. Okay, so 0 by 2, 7 by 1 whole divided by 1 by 4 plus 1 by 2 plus 1 by 1. Okay, so you just simplify it, you will get 8 volts. Okay, so what is this 8 volts? It is the equivalent voltage across, so means all these voltage sources which are connected in parallel. Of course, there is no source here, but assuming that there is a voltage source whose value is 0, EB2, I might have drawn here voltage source EB2 with 0 volts. Okay, that I might have done that. So I will just, okay, what should I do? I can do that. I will just copy it. I can do that. I will do that. So I just for a second, don't worry, it won't take much time. You people can also copy it down in your notes. Okay, this is it. So see here, to be more specific and so that you can understand this equation which I have written here from this circuit. Okay, so here I have written EB2. It is not there, but I have assumed EB2. Okay, so it is connected in the circuit, and this EB2 value is how much? 0 volts. Okay, so if you want, you can draw and you can mention that it is 0 volts. So it means that there is no source at all. If you write 0 volts, what does it mean? Voltage is 0, source voltage is 0. So you can do that. So 28 by 4 plus 0 by 2 plus 7 by 1 whole divided by 1 by 4 plus 1 by 2 plus 1 by 1. So this is it. In this circuit itself, it is there. All the elements are there. You can directly, I hope you are able to follow. So what is our equivalent voltage source value? Now it is 8 volts. So what is the voltage across equivalent voltage meant? It is the in the parallel branch, voltage across the parallel branch. So always remember, if the voltage across the parallel branches will be always same. Okay, current in a series branch will be same. Okay, current through any element in a series branch will be same, whatever may be the resistance value. But similarly, voltage across parallel branches will also be same. So this is our equivalent voltage, that is 8 volts that I have mentioned here. Okay, now I hope you have understood. Okay, so now same thing I have written here once again. It was not required. Same thing I have written. I have written it twice. Acha. No. Yeah, I have written it twice. Equivalent voltage. It is already, I already wrote in the previous slide, and once again in the second slide also I have kept it. Okay. Now let us determine the voltage across R1. What is the voltage across this R1? This is our R1. I have simply copied from the previous slide. No need to copy. So now to explain you how to determine the voltage across R1, I have just copied from the previous slide. So what is the voltage? What is the resistance? R1 value 4 ohms. Okay. So if I want to determine the voltage, okay, see what is the total voltage in this branch? In this branch, what is the total voltage? Total voltage is EB1 plus voltage across R1. Okay. So let us assume voltage across R1 is ER1. Voltage across R1 is how much? ER1. Okay. So I might write here ER1. Okay, voltage across R1 is ER1. So what is the total voltage? Equivalent voltage that we have obtained, that is 8. Equivalent voltage is 8. So 8 will be equal to equivalent voltage is 8. So parallel branch. These are the parallel branches. This branch, and this branch. These three are the parallel branches. Okay. Therefore 8 is the equivalent voltage, isn't it? So 8 is equal to sum of the voltages in this branch. What are the sum of the voltages? Or EB1 plus ER1. EB1 plus ER1. So what is EB1 value? 28 volts. Okay. EB1 value is 28 volts. That I didn't write here. So if you want, you can write it there. EB1 plus I can write one more term here. I will write it so that it will be more clearer to you. This is it. This is the equation. ER1 voltage across R1 is ER1. ER1 plus EB1 should be equal to E equivalent. ER1 plus EB1 should be equal to E equivalent. So what is ER1? We don't know. What is EB1? 28 is equal to E equivalent is equal to how much? 8. So ER1 plus 28 is equal to 8. So what is ER1? 8 minus 28. What is ER1? Minus 20 volts. So this is the voltage across R1. No need to draw the circuit. You can just write down the equations and we will proceed further to determine the voltage across I hope you might have written already. So let us proceed further to determine the voltage across R2. Okay, now let us see what is the voltage across R2. Let us assume the notation for that voltage is ER2. Voltage across R2 I want the voltage across R2. And so let us assume no voltage across R2 is ER2. So ER2 plus, this is it, ER2 plus EB2 is equal to what? 8. ER2 plus EB2 is equal to 8 volts. So because 8 is the equivalent voltage, okay, 8 is the equivalent voltage. So therefore 8 is equal to, or ER2 plus EB2 is equal to E equivalent. What is ER2? I don't know. I have to determine. What is EB2? EB2 is not at all there. We have assumed 0 voltage. Okay. So we have assumed a voltage source whose value is 0. So ER2 plus 0 is equal to what? 8. So ER2 is equal to 8 minus 0, ER2 is equal to 8 volts. ER2 is equal to 8 volts. This is it. Now let us determine the voltage across this third branch. Okay, let us determine the voltage across this branch. My cursor, it won't listen to me. Okay, so what is the voltage across third branch? EB3 plus ER3, that is equal to the equivalent voltage, that is 8 volts. So ER3 plus EB3 is equal to E equivalent. So ER3 I don't know, I have to determine. EB3 is how much? 7 volts. So EB3 is 7. What is equivalent voltage? That is 8. So ER3 is equal to 8 minus 7, that is ER3 is equal to 1 volt. So write it down. As soon as you complete, just inform. So here we have determined the voltages across each resistor, that is the internal resistance of the sources. But in the question they have asked us to find the current through each resistor. They didn't ask us the resistance voltage across the resistor, but they have asked us to determine the current flowing through each resistor. So let us determine the current flowing through each resistor. Okay, so let us determine the current flowing through each resistor. So just now we have determined, I will just copy this, no need to copy actually. Okay, so what is the voltage across ER1? It is 20 volts, isn't it? 20 volts. Okay, I might have written that ER1 divided by R1, isn't it? That might have been more better. So I will write that. It might have been more better. I will just write that. Okay, I couldn't copy that. I wanted to write something, but I couldn't copy that. Wait. I already have. ER1 by R1 is equal to ER1 is 20, R1 is 4. So you will get 5 amperes. Similarly, ER2 by R2. That's it. Over. They have asked us to determine the current. So I thought if I specifically mention the notations here, it will be more easy for you to compare and it will be easy for you to understand. That's it. So what is the current flowing through R1? Voltage across R1 by resistance value. So ER1, current through R1 is, ER1 value is 20, R1 is 4. Simplify it, you will get 5 amperes. Similarly, current through R2 is what? Voltage across R2 divided by resistance value, R2 value. ER2 value 8 volts, R2 value is 2 ohms. So just divide this, you will get 4 amperes. Similarly, IR3 is ER3 by R3. So ER3 value is 1 volt. ER3 value is 1 volt and R3 value is 1 ohm. So just divide it, you will get 1 ampere. So this is it. As soon as you complete, inform. So we will solve one more numerical problem and we will go for Tellegen's theorem. Okay, I hope you might have completed that numerical problem. So let us proceed further. Next problem. Using Milliman's theorem, find the current IL. So see here in this circuit, IL and current IL through RL. Okay, this is RL for the network shown in the figure. Okay, this is a given figure. So you can see this is more this circuit which has been given to us. This circuit is more easy to understand to solve this circuit using Milliman's theorem, isn't it? All the voltage sources are there and their internal resistances, load resistance is there. Okay, so clearly mentioned. So you just take a minute, you just draw the circuit, write down the question and draw the circuit quickly. So I hope you have completed. So here what you can see, there is a voltage source of 10 volts, another voltage source of 20 volts, another voltage source of 30 volts. In series to 10 volts there is 2 ohms resistor, and in series to 20 volts there is another resistor of 3 ohms. In series to this voltage source there is another resistor of 4 ohms, and there is a load resistor here. So now let us solve this numerical problem. So first of all, what is the resistance in each branch? You just write it down. R1 value 2 ohms, R2 value 3 ohms, R3 value 4 ohms. 2 ohms, 3 ohms and 4 ohms. So let us give the notations. I didn't redraw the circuit here, but I have just given notations to 2 ohms. 2 ohms is R1, 3 ohms is R2 and 4 ohms is R3. Now what is the conductance in each branch? Conductance means reciprocal of resistance. Conductance is reciprocal of resistance. So 1 by R1 is G1, 1 by R2 is G2, 1 by R3 is G3. So determine the conductance. So 1 by 2, 1 by 3. This is another method. Okay. So we can follow the same method which we have earlier followed. So you can follow the same method. I have followed one more method. I thought 2 methods. If you know 2 methods, then your wish, whichever method you want to follow to solve the numerical problem, you can follow that. So for that reason, I'm solving one more numerical problem which means I'm using here conductance instead of directly I can use the resistance. I can solve the numerical problem to determine the IL current. But just for namesake, if 2 methods are there, some people, the way they think, everyone won't think in the same pattern, isn't it? So some people may follow the first method, they may like the first method, some people may like the second method. So that's why I'm solving these numerical problems, one in one method and the second one in the other method. So let us see the second method, how to solve the same numerical problem using Milliman's theorem. So here I have determined the conductance value G1, G2, G3. G1 is 1 by R1, 1 by 2 is 0.5 mho. G2 is 1 by R2, that is 1 by 3. R2 is 3 ohms. So 1 by 3 is 0.33 mho. G3 is 1 by R3. So 1 by 4. R3 is 4 ohms. So 1 by 4 is 0.25 mho. So I hope you might have written till now. Okay. So by now you might have completed. So I'm going for next slide. So now what is the total conductance? We have determined the conductance of each branch. So total conductance is, that is equivalent conductance is G1 plus G2 plus G3. So what is G1? 0.5. G2 is 0.33. G3 is 0.25. Okay. So add them, you will get equivalent conductance. So now what is the resistance, equivalent resistance, reciprocal of conductance? So what is it? 0.923. Okay. Just write it down. Okay, I hope you might have written. So now, what is the equivalent voltage here? I have considered this is the first voltage source value. Okay, so let us assume first voltage source is some E1 into G1 plus E2 into G2 plus E3 into G3. So I didn't write E1, E2, E3. If you want, you can write. Consider this as E1. I can't write E1, isn't it? My cursor won't listen to me. So consider this as E1, consider this as E2, this source notation. Okay, this as E3. Okay, so notations for each source, E1, E2 and E3. So E1 into G, okay, G1, E1 into G1, E2 into G2, E3 into G3. whole divided by G1 plus G2 plus G3. So you know G1, G2, G3 values, you just substitute it and determine the equivalent voltage. That is 17.689 you will get, 689 volts you will get. So I hope you might have completed writing it down in your notes. You might have written in your notes. Okay then, I'm proceeding further. So you have got E equivalent, just now we have calculated, that is 17.689. Already we have calculated R equivalent. You can write down that. So this is our Milliman's equivalent circuit. R equivalent, E equivalent connected across the load. So draw the Milliman's equivalent circuit. Draw the Milliman's equivalent circuit. In the previous numerical problem, there was no load, so that's why we didn't even draw the Milliman's equivalent circuit. Here, there is a load and they have asked us to determine the load current. So that's why I have drawn this Milliman's equivalent circuit now. Okay, so this is the equivalent circuit. So from that circuit, you can determine the load current. I will just copy this circuit in the next slide to determine the load current. So here what is IL? IL is equal to what? Total voltage. In this circuit, it's a single loop circuit, you can see. So total voltage in this equivalent circuit is E equivalent. E equivalent by total resistance. Req and RL both are connected in series, isn't it? R equivalent and RL are connected in series in this circuit. Okay. So E equivalent by R equivalent plus RL. So E equivalent is how much? How much is R equivalent? R equivalent, I think I wrote something. Something is wrong here. I didn't write the correct terms. So what is this? R equivalent value is 0. This is wrong. 0.923. So you people check the answer. Whether my answer is right or wrong, you just check it and tell me. Yeah, so earlier what I wrote, it was wrong. So by mistake I wrote the E equivalent value here in the denominator. So this is E equivalent 17.689 divided by R equivalent 0.923 plus RL value is 10. So IL is equal to 1.6 amperes. So that's it. This is about Milliman's theorem. I hope you have understood. Okay. So now let us see Tellegen's theorem. So let us see what is meant by Tellegen's theorem. What is this S? There is something wrong with this S. There is something wrong with this. Some question mark is there here. Maybe it is the design of this slide is like that. Maybe I don't know. Okay. Now let us see what is meant by Tellegen's theorem. So this is yes. Okay. So some question mark is there which I am unable to delete there. So let us see Tellegen theorem. So this theorem states that in a given network, the algebraic sum of all the powers delivered by all the sources is equal to the algebraic sum of all the powers absorbed by all the elements. Okay. So if you have n number of sources in the given circuit, if you add all the powers delivered by the sources, that should be equal to the n number of passive elements which are there. If you calculate the power across each and every element, then that should be equal to the sum of the powers absorbed by all the elements. So for to understand that, I don't think I don't have any circuit here. Okay. So simply you try to understand it. So powers delivered. Okay, I have a numerical problem. If you go through that problem, it will be easy. You can easily understand. Algebraic sum of powers delivered by the sources is equal to sum of powers absorbed by all the passive elements. So passive elements absorb the power. Okay, passive elements absorb the power, and the active elements deliver the power. So sum of the powers delivered should be equal to the sum of the powers absorbed by all the elements. So let us see. So let us see a numerical problem. So you just write it down first of all. You just write it down. In other words, I can say that algebraic sum of all powers in all branches at any instant is equal to 0. That is one more statement for this Tellegen's theorem. One more statement is algebraic sum of all powers means algebraic sum of powers in all branches at any instant is equal to 0. Okay, and these branches, okay, the branch currents and voltages across each branch, they must satisfy the Kirchhoff's voltage law. Okay, so let us go to the numerical problem. So in this numerical problem, using Tellegen's theorem, find the voltage across 6 amperes. current source. Okay, voltage across 6 amperes current source is asking for the following circuit. So you have to determine the voltage across 6 amperes current source. It's a very simple and small problem. You can see there is a current source, there is a voltage source, there are two resistive elements, means two power absorbing elements, two power delivering elements. Okay, power delivering elements are 12 volts voltage source and 6 amperes current source. Two sources are there. So how many powers are delivered here? Two powers. Okay, two sources, two powers are delivered. Two passive elements, two resistors are there. So how many powers are absorbed? Two powers are absorbed. So algebraic sum of two powers delivered must be equal to the algebraic sum of two powers absorbed. Okay, algebraic sum of two powers delivered must be equal to the algebraic sum of two powers absorbed. That's what we have to satisfy. And of course, they didn't ask us to verify Tellegen's theorem. Of course, I am going to verify Tellegen's theorem for some other circuit. I will make that video and I will I may take a live class on that later on. It's a bit big circuit that I will discuss. For that I have prepared the manual. That manual also I will upload it later. And after uploading the manual, we will perform the theoretical calculations. So for those theoretical calculations, while discussing about So while discussing about the theoretical calculations, or for doing the theoretical calculations, okay. So I will verify Tellegen theorem for the theoretical calculations for the manual that is available in my channel. So I have not even, it is there in my channel, but I didn't make it public. It is still in private session. Okay. So as soon as I make it public, the Tellegen's theorem manual, I will take an online class to verify Tellegen's theorem for that particular circuit which I have shown in the laboratory manual. Okay. So meanwhile I was talking, you might have drawn this circuit, you might have written this question. So let us proceed. So here let us see how many branches are there. Total 3 branches, branch 1, branch 2 and branch 3. 3 branches are there. Okay. And what is the source current? Source current is 6 amperes. Source voltage is 12 volts. I have assumed 2 loops. Okay, I have assumed 2 loop currents. So mesh 1. Okay, I can't write mesh 1. I don't want to write at all. So I have assumed 2 loop currents, I1 and I2 here. I1 is in clockwise, I2 is in anti-clockwise. Your wish, you can assume any direction. So I1 is in clockwise, I2 is in anti-clockwise direction. Now we have to determine I1 current and I2 current. Now consider mesh 1. This is mesh 1. What is our loop current? I1. So if you see in this mesh 1, what is there? Current source is there. So no need to determine the loop current. Loop current is nothing but the source current value. So I1 is equal to what? Okay. Hey, this cursor, I don't know why. I1 is equal to 6 amperes. So what is I1 is equal to? 6 amperes. Why I1 is equal to 6 amperes? Because whenever in a loop current source is there, that loop current value is nothing but current source value. So I1 is equal to 6 amperes. Now I have determined the I1 current. Of course, I didn't determine, already it was there. So simply I wrote it. Now apply KVL in loop 2. So in loop 2, what is there? There is a voltage source, there is resistor R2, there is resistor R1. So what is it? 12 is equal to, source voltage is equal to R2 into I2. R2 into I2, voltage drop across R2. So R2 into I2 plus R1 into R1. Okay, R1 into, if you observe, I2 is downward, I1 is also downward, means I1 and I2 are in same direction. So the currents will add R1 into I1 plus I2. So 12 is equal to R2 into I2 plus R1 into I1 plus I2. What is R2 value? 2 ohms. R1 value 6 ohms. So 12 is equal to 2I2 plus 6I2 plus I1. So simplify it further. 2i2 plus 6i2 plus 6i1 equal to 12. Okay. And 6i1 plus 8i2 is equal to 12. That's what you will get if you further simplify. Okay. This is one expression that you have got. Okay. So just write it down. Write it down. I hope you are able to follow. If you are listening, you will be able to follow. I am trying to teach in the as simpler possible way as possible. So so Mr. Ashish, you are giving me orders. No respect for the staff who is teaching you. Ashish. So what is I1 value? I1 value is 6 amperes, isn't it? I1 value is 6 amperes. So you have an expression here. What is that expression? 6i1 plus 8i2 is equal to 12. So what is I1 value? 6 amperes. I1 value is 6 amperes. So instead of I1, substitute 6. So 6 into 6 plus 8i2 is equal to 12. Okay, 6 into 6 plus 8i2 is equal to 12. You just simplify it, you will get the I2 value. Okay, just simplify it. So 6 into 6 is 36 plus 8 into I2 is equal to 12. So send 36 to the other side. 8 into I2 is equal to 12 minus 36. So 8i2 is equal to 12 minus 36, you will get minus 24. I2 you will get minus 3 amperes. Okay, so I2 is minus 3 amperes. So what is the current flowing through the middle branch? That is branch 2. What is the current? Both the currents are adding, isn't it? I1 plus I2. So I add I1 current is 6. I2 we have got minus 3. So what is the current in branch 2? It is 3 amperes. So current in 6 ohms is how much? 3 amperes. It's okay, Ashish. You are habituated to speak like that, it seems, huh? It's okay. No need to say sorry. It's just, I felt as if you are giving me orders. That's it. So I hope you have understood, all of you. Just note it down as quickly as possible, and I will conclude this class within 5 minutes. So I hope you might have completed. So current in second branch is 3 amperes. Okay. What about current in first branch? It is 6 amperes. I1 current. Okay. So what is I2 current? Current in third branch? It is minus 3 amperes. Okay. So that's it. Now let us consider, already we have considered the loop currents, isn't it? I1 loop current and I2 loop current. Let us even consider the node voltage also, V. V is our node voltage at this node. I am assuming some node voltage V. So node voltage and loop currents. Okay. Now we have to first of all calculate the powers delivered by the sources. How many sources are there? Two sources. So power delivered by current source, that is P 6 amperes. Power delivered by voltage source, that is P 12 volts. Okay. So power delivered by current source and power delivered by voltage source. That I might have written here itself. It might have been better. Power delivered by current source. I can write it here. It's okay. I will try to write. So I think this is more clearer and specific. I will make this bold. So power delivered by the sources we have to calculate. So power delivered by the current source. What is the power delivered by the current source? See here. This is our node voltage. Let us, we have assumed node voltage. So I know current. Okay. I don't know the voltage value. Node voltage, if I might have known the node voltage, voltage into current, that will might have given me the power value. Okay, so I don't know the voltage. So what is power delivered by the current source? V, node voltage V into I1. I1 is nothing but source current, 6 amperes. Okay. So I have written some notation I1, but I might have written IS, even source current is IS. Okay, so I might have written that, but I have written I1. I1 or IS, both are same. Okay, so V into 6, current is 6. So 6 into V or V into 6, both are same. Okay, so now power delivered by the voltage source. There is a voltage source here. What is the power delivered by voltage source? V into I. What is I in this branch? Branch 3 current is I2 current. What is I2 current? Minus 3. So 12 into I2, 12 into minus 3. You will get minus 36 watts. Okay. So here we don't know V value, node voltage, and even in the question what did they ask? They have asked us to determine what? They have asked us to determine the voltage across 6 amperes current source. Okay, so we don't know that, we will determine that. So this is the power delivered by current source, this is the power delivered by the voltage source. Next we have to determine the power absorbed by the elements. What are all the elements here? 2 resistors are there. So let us determine the powers delivered by the resistive elements. For that I will copy this circuit in the next slide. Now powers absorbed by the passive elements in the circuit. Okay, what are all the passive elements? 2. One is resistor R1. Other is resistor R2. Okay, resistor R1 and resistor R2. Okay, so what is the power absorbed by R1? So power absorbed by R1 is how much? Okay, power formula, if you have resistor and if you know the current formula is I square R. Okay, power equation, or V square by R. So since we have already determined the current, so we will go for I square R formula to determine the power. So power in R1, okay, PR1 is equal to R1 into I square. I square. What is I in branch 2? What is the current in branch 2? Just now we have calculated. It was 3 amperes, isn't it? I will just check. What did we get? Current in 6 ohms is 3 amperes. Yeah. So current in 6 ohms is 3 amperes. So what is it? This is our branch, 6 ohms resistor. So R1 into current in 6 ohms square. So 6 into 3 square, you will get some 54 watts. And what is R2? Power in R2. So this is our R2. What is the power? So I into I square r, I can say I square r or r into I square. So R2 value is 2. 2 into what is current? This current is minus 3. So 2 into minus 3 square, you will get 18 watts. Okay, so power absorbed by R1 is I square r value you have got 54. Power absorbed by the R2 I square r we have got 18 watts. Okay, so we have determined the power delivered by both the sources. We have determined power absorbed by both the passive elements here. So no need to draw this circuit again and again. I have simply copied here to just to show you. Okay, in order to show you the elements. Okay, so across which power is absorbed. In order to show that, I have copied from the previous slide. No need to copy it here. So just I hope you might have written. Okay, you might have written. Now according to Tellegen's theorem, what is it? Powers. According to Tellegen's theorem, total power delivered must be equal to the total power absorbed. Algebraic sum of powers delivered in the given circuit must be equal to the algebraic sum of powers absorbed in the circuit. So what are the powers that are delivered? Two sources are there. Two powers are delivered. What are those powers? P6A plus P12V. So these notations are our wish. We can write anything that we want. So power delivered by the current source plus power delivered by the voltage source, that is equal to power absorbed by resistor R1 plus power absorbed by resistor R2. Okay, that is it. Total power delivered in the circuit is equal to the total power absorbed by the passive elements of the circuit. So power delivered by the current source, how much? 6 into V. Okay, I into R. Sorry. V into I. Okay, so I don't know V value, I know I value is 6. So what about the power delivered by this source? We have already calculated, that is minus 36. Okay, power delivered by 12 volts voltage source, that is minus 36. And power absorbed by R1 is 54, power absorbed by R2 is 18. So just solve it. 6 into V minus 36, 54 plus 18. I have written it twice, it seems. Yeah, I have written it twice. Same thing I have written it twice. No need to write again and again. I have written it twice. So 6 into V is equal to, you just send this minus 36 to the other side. It will become plus 36. You just add it and divide it by 6. Okay, you will get the V is equal to some 18 volts. So what is the voltage across 6 amperes current source? That is 18 volts. Okay. So that's it. I hope I was able to explain this both the Milliman's theorem and Tellegen's theorem in as simpler way as possible. I hope you have understood. If you have any confusion, you can once again go through this video and listen to the lecture once again. You may get some clarity on these two topics. So if you want any other lecture on any other concept related to this circuits, electrical circuits, you can mention in the chat box. I will deliver a lecture on that. Okay, I will deliver the lecture on that particular topic. So okay, then this session is over.